Every time your browser opens a secure connection to your bank, to your email, to any website with a padlock in the corner, your computer performs a mathematical task in the background that took humanity 2,000 years to figure out how to do correctly. It checks whether a number is prime, not a small number, a number with 300 digits, sometimes 600, and it does this check in under a millisecond, dozens of times per session, without you ever noticing. The definition of a prime is something a child can memorize. A prime number is one that cannot be divided evenly by anything except 1 and itself. 2, 3, 5, 7, 11, 13. The sequence is simple to describe and maddeningly hard to predict. There is no formula that generates all primes. There is no pattern that tells you where the next one will appear. They thin out as numbers get large, but they never stop. Euclid proved that in 300 BC, with an argument short enough to fit on an index card. The problem is not definition. The problem is scale. To check whether 7 is prime, you test whether 2, 3, 4, 5, or 6 divide it. 5 checks. Done. To check whether the 1,000,000th prime, 15,485,863, is prime, you need to test every integer up to its square root, which is about 3,935. A few thousand checks. A modern computer handles that instantly. Now try a 300-digit number. The square root of a 300-digit number has 150 digits. The number of integers you would need to check by trial division is larger than the estimated number of atoms in the observable universe. A computer checking 1 billion candidates per second would not finish before the sun burns out. Ethernet encryption, the protocol underlying essentially all secure internet traffic, is built on the fact that large numbers are hard to factor. Finding large primes is the first step in building an RSA key. When you generate a new private key, your computer needs to find 2 primes, each around 1024 bits long, which works out to roughly 300 decimal digits each. It needs to do this quickly. Trial division is not a solution. For most of history, this was not a problem anyone needed to solve, because no one needed large primes for anything practical. Then the 1970s happened, and suddenly the entire digital economy needed an answer. The first real shortcut came from Pierre de Fermat in 1640, who was not thinking about computers or cryptography. He was thinking about patterns in remainders. His little theorem states a clean fact. If p is prime, then for any integer a that shares no common factor with p, a raised to the power p minus 1 leaves a remainder of 1 when divided by p. Written as a congruence, a to the power p minus 1 is congruent to 1 modulo p. This is useful because it gives you something to check. Take a large candidate number n, pick a random value of a, compute a to the power n minus 1 modulo n. If the result is not 1, n is definitely composite. You have found a witness to its compositeness. If the result is 1, n might be prime. That word might is the problem. The test is not reversible. There exist composite numbers that pass Fermat's test for every single value of a. They fool the theorem completely. These are called Carmichael numbers, after Robert Carmichael, who catalogued the first of them in 1910. The smallest Carmichael number is 561. It equals 3 times 11 times 17. It is obviously composite. And yet, for every value of a with no common factor with 561, the Fermat test returns 1. The number 561 is wearing a prime costume that Fermat's theorem cannot see through. Carmichael numbers are rare, but they are infinite in number, and their existence means no refinement of the Fermat test can ever be made deterministic. The Miller-Rabin test, developed independently by Gary Miller in 1976 and Michael Rabin in 1980, attacks the problem differently. It adds a second layer of checking based on square roots of unity modulo n, a condition that composite numbers have a much harder time faking. A composite number can still pass Miller-Rabin for any specific witness, but the probability of passing is at most 1 in 4. Run the test with 40 independent random witnesses, and the probability of a composite number fooling all 40 is at most 4 to the negative 40th power, roughly 1 in 10 to the 24th. You are more likely to be struck by lightning twice in the same second than to encounter a Miller-Rabin false positive in a lifetime of computation. This is the test your browser uses right now. It is the test your phone uses. It underlies every SSL certificate, every encrypted message, every secure login on the internet. Fast, practical, and technically not guaranteed to be right. In the 1960s and 70s, theoretical computer scientists began building a formal vocabulary for talking about the difficulty of problems. The class P contains all problems that can be solved in polynomial time, meaning the number of computational steps required grows as some power of the input size. If the input is n digits long, a polynomial time algorithm might take n squared steps, or n cubed, or n to the fifth, but the exponent is fixed. The class NP contains problems whose solutions, once found, can be verified in polynomial time, even if finding the solution in the first place might require exponential time. P versus NP, the question of whether every efficiently verifiable problem is also efficiently solvable, became the central unsolved problem of computer science. It remains unsolved. But adjacent to it sat a narrower question with a cleaner statement. Where does primality testing live in this landscape? Primality is clearly in NP. If someone hands you a prime number and claims it is prime, there exist mathematical certificates, called Pratt certificates, that allow you to verify the claim in polynomial time. Verification is easy. The question was whether deciding, computing the answer from scratch, was also easy in the polynomial time sense. There was a conditional answer. In 1976, Gary Miller proved that a deterministic version of his primality test runs in polynomial time, assuming the truth of the generalized Riemann hypothesis. This is one of the most important unproven conjectures in all of mathematics, connected to the distribution of prime numbers and worth $1 million Millennium Prize. The conditional result was clean and promising. The condition itself was unverified and remained so. So for more than 2 decades after Miller's result, the situation was unresolved. You had a fast probabilistic test that worked in practice. You had a fast deterministic test that worked given an assumption no one could prove. And you had a fundamental open question. Is there an unconditional deterministic polynomial time algorithm for primality testing? And if so, what does it look like? On August 6, 2002, a paper appeared on the preprint server Archive. It was 9 pages long. Its title was 4 words, Primes is in P. The authors were Manindra Agrawal, a professor at the Indian Institute of Technology Kanpur, and 2 of his undergraduate students, Neeraj Kayal and Nitin Saxena. Kayal and Saxena were 22 years old. The core of the algorithm rests on a polynomial identity. For a prime P and an integer a with no common factor, the following holds in the polynomial ring over the integers modulo p. X minus a raised to the pth power is congruent to x to the p minus a modulo p. This is a generalization of Fermat's little theorem lifted into the world of polynomials. Instead of checking a single numerical identity, AKS checks whether an entire polynomial equation holds. The crucial observation is that this identity holds for all primes and fails for almost all composites, and the failure can be detected efficiently. The algorithm works roughly as follows. First, find a small prime r such that the order of n modulo r is large, specifically larger than the square root of r times the logarithm of n. Then, for each value of a from 1 up to the square root of r times the logarithm of n, check whether the polynomial identity holds modulo both x to the r-1 and n. If all checks pass, n is prime. The number of checks required grows as roughly the square of the logarithm of n. Each check involves polynomial multiplication in a ring of bounded degree, which takes polynomial time. The total running time is order of log n to the 6th power, meaning the number of steps is bounded by some constant times the 6th power of the number of digits in n. That is polynomial in the number of digits. That is what p means. The proof was confirmed by researchers around the world within days of the paper appearing. It won the Gödel Prize in Theoretical Computer Science in 2006. It answered a question that had been open since the complexity theoretic framework was invented. Primes is in P, definitively, unconditionally, without assuming anything about the Riemann hypothesis. A pair of undergraduates and their professor had closed the case. And AKS is not used in practice. Not in your browser, not in cryptographic software, not in any production system that has been publicly documented. The algorithm that proved primes is in P has been in the mathematical literature for more than 20 years, and the practical world has largely ignored it. The reason lives in the gap between big O notation and actual running time. When we say AKS runs in order of log n to the sixth, we mean the running time is bounded above by some constant multiplied by log n to the sixth. The big O notation hides the constant. It tells you how the algorithm scales with input size, not how long any particular run takes. In practice, the hidden constant in AKS is large. The polynomial is clean on paper and slow on hardware. Miller-Rabin with k witnesses runs in order of k times log n cubed with a much smaller constant. For a 300-digit prime, the kind used in RSA, the difference in actual wall clock time is several orders of magnitude. Miller-Rabin finishes in microseconds. AKS takes far longer. From a cryptographic standpoint, this is not a close contest. There is also the BPSW test, published in 1980 by Bailey, Pomerantz, Selfridge, and Wagstaff. It combines a Miller-Rabin step with a Lucas probable prime test using a different mathematical structure. The two tests are independent enough that a composite number fooling both simultaneously would require a very specific and unusual structure. As of 2026, no BPSW pseudoprime has ever been found, not one for any number any computer has ever tested. The theoretical possibility exists, no one has proven it cannot happen, but it has never been observed. In cryptographic engineering, no counterexample has been found in 46 years of searching, and the probability is astronomically small is considered good enough. The algorithm is fast, the error probability is negligible, and no practical issue has ever been reported. And so AKS sits in journals while the world runs on probabilistic tests. The perfect algorithm loses to the practical one. It is not a close race. There is a version of this story where AKS is a triumph with no asterisk, a genuine open problem in theoretical computer science resolved in 9 pages with undergraduate co-authors, 0 precedent and 0 errors. That version is also the true version. Nothing about the practical outcome changes what was mathematically achieved, but the gap between what was proven and what is used illustrates something important about the relationship between theory and practice in mathematics and computation. Polynomial time is a theoretical guarantee about scaling behavior. It says, as the input grows, the running time grows no faster than a fixed polynomial. It does not say anything about how fast the algorithm runs today on this machine, on this input. A polynomial time algorithm with a large constant factor can be slower than an exponential time algorithm with a tiny constant factor for every practical input size ever encountered. The P versus NP problem, if resolved in favor of P equals NP, would guarantee polynomial time algorithms for thousands of currently hard problems. It would not guarantee that those algorithms are useful. An algorithm running in n to the 1000th power time is technically polynomial. It would be useless. This is a feature, not a flaw. Complexity theory is not engineering. It answers questions about what is fundamentally possible, about the shape of the computational universe, not about what will ship in the next software release. AKS answered a question about fundamental possibility. Whether that answer matters for cryptographic practice is a separate question with a separate answer. Both questions are worth asking. They just have different answers. The largest known prime, as of 2024, has 41,024,320 digits. It is a Mersenne prime, a prime of the form 2 raised to some prime exponent minus 1. The exponent is 136,279,841. To verify it, researchers used a specialized algorithm called Lucas-Lehmer, developed in the 19th and early 20th centuries, designed specifically for numbers of this form. AKS could verify it. The algorithm is general, it works for any number in polynomial time with certainty. The calculation would just take much longer. We have in our hands an algorithm that answers one of the oldest questions in mathematics. Is this number prime? For any number in a bounded and predictable amount of time with absolute certainty. It was discovered by a professor and two undergraduates in Kanpur in 2002. The world continued using the probabilistic test. This is not a tragedy. The Miller-Rabin test is fast, and in the 4+ decades it has been deployed, it has never once returned a wrong answer for any cryptographic prime that mattered. The BPSW test, more than 40 years old, has no known counterexample. These are not perfect guarantees. They are something arguably more robust, empirical records, tested against every adversary who has ever tried to find a crack in them. Mathematics draws lines in the logical landscape regardless of whether anyone crosses them. The line AKS drew, primes is in P, certainly, unconditionally, for all time is real. Whether you cross it on any given Tuesday depends entirely on what you are trying to do. The algorithm exists. It works. Nobody uses it. All three of those facts are completely fine.